All right, an excited state is what happens when you put energy into an atom. I'll show you in a demonstration next time, but if you add energy to an atom, okay, these electrons, these little yellow fuzzballs, can take that energy and jump up to higher places in the hotel because they have energy to help them move. And then we have what is known as an excited state, where they've moved up higher than they should have, which will often or will leave holes in the lower states. So an excited state configuration looks like it's breaking all the rules because there's holes, you're jumping around because it's taking in energy. I'm going to give you an example of an excited state 1. You do not need to know how to write an excited state. You just need to know how to identify that it is one, because the options are infinite almost of like where it can jump. Okay, so an excited state, let's define it, is when the electrons, remember E negative is like the symbol for an electron. Okay, the electrons take in energy, and I guess I'll say outside energy. Now by energy, this could be like heating it up. So if you heat something up enough, it can do this. Electrical energy, so if I send electricity through it, that can cause it to happen. Okay, so the electron takes in outside energy and move to higher levels. So if our little model could do this, I'd put energy into it and we'd see the little yellow ones jump up to the other rings that aren't even modeled but are there. Okay, so for carbon, an excited state could look like 1s1, 2s1, 2p2, 4s1, let's go crazy, 5p1. Right, like they just start jumping up. There is something that's the same between the excited and the ground. What's the same about them? Emily?
They still add up to 6.
Yeah, like the electrons don't go away. There's still 6 electrons total, 2, 4, 6, right? So that's kind of one way you could know, like, oh, it's still carbon, but they're in higher states because of the energy. Now, just like everything in life, what jumps up must eventually come back down. They don't stay in an excited state. Eventually, once the energy is taken away or whatnot, they'll fall back to the ground and give that energy back out. But that's just, if you were to see something like this, don't stress and just be like, oh, that's an excited state because it's crazy. Okay, questions on what that means? Okay, let's go down to the section now that talks about the ion configuration. So same idea, but now the difference is now we're looking at the removal or the addition of an electron. So if instead our calcium ion had a positive 2 charge, how would its configuration of electrons change? So the first thing to remember is if something is positively charged, what does that mean about its electron count?
It has 2 minus.
Good, so it has less, which means plus 2 means lost 2 electrons. Right, 2 electrons were taken for bonding or whatever purpose, and they're not there in that calcium anymore. So the configuration should support how many electrons are actually there. So in this case, if 2 were lost, what happened to this 4s? It was emptied, right? It's not there anymore. In a sense, that shell was peeled away, and so what's left is argon. Now we can't just write argon in brackets and call it a configuration, but we can write it shortcutted still. So I would do Ne and then 3s2, 3p6. Questions on that? So we just removed the electrons and then fixed it because since the shortcut. Person.
How would that change the calcium?
Great question. So he asked, how would that change the calcium itself? So what we'll learn about, and this is really the whole year, is electrons are what cause chemical reactivity. I remember last time, was the last time or time before, right? We had the hydrogen peroxide and I put in water, and one of them made a cloud, and one of them did nothing, right? It's all about your electrons changing. And so that's the same thing here, is actually this ion of calcium is very, very stable because of its new configuration.
It's a full shell. So
Yeah, because that full shell makes it quite stable. So we would say that this is, you don't need to know it, but it's isoelectronic to argon, because it looks just like argon does in electron form. It's not argon, but it looks the same, but it makes it quite stable. For example, when we say like we need calcium, right? Like calcium's good for you, right? Like it's good for your bones. This isn't the calcium we're saying. You eat this calcium, your tongue will explode. Like, and it would not be good for your body because we don't digest metals well. The ion form of calcium, that's what your body needs. It needs calcium ions because they don't react in negative ways and they just add to your calcium of your bones. So, great question, Bryce. Have a smile for your side. Okay, let's come to this one. It gets a little bit weirder when you have multiple orbitals to pick from. So we now have Mn2+. So the same idea, we're losing 2. But do they get removed from the 3D, or the 4s is then kind of where we're the difference from before? And the answer is when you have multiple orbitals to pick from, they always get removed from the highest orbital first. And by highest, I mean 4 is higher than 3. So even though we fill the 4s first, that's the one that gets removed from first. So this would actually go away, and your configuration would be AR 3D5. So the higher energy level, right, is what we remove from. You can obviously think once again, because it's just, if there's a 4th ring on this, it's easier to pull off that 4th ring than to like get inside that 3rd ring and pull those ones off. Questions on that? All right, and then on the negative side, so if fluorine has a -1 charge, negative now means we're going to add to the orbitals, and so we just look for the open spot. In this case, the P has 1 more, and so it would be He, 2s2, 2p6. So whenever I'm asked to do a configuration of an ion, so if it's charged, I always think about, okay, what's the original, write that first, and then adapt it accordingly. So, questions on that?
That's a stable fluorine, right?
Yep. All these are actually more stable than they were before. Which is typically, that's the only reason why they ever would become an ion, so. Yeah.
Do you still remove from the highest level if there's another orbital that isn't completely filled yet, or?
Can you give me an example, maybe what you're asking, Zach?
Like if you have if you're still filling like the 2 like D orbital or 3D orbital, like and you have like 2, 7, would you still take it away from the, the higher orbital?
Yep. Yep, if I'm understanding your question, yep, it always is gonna be, because even this D's not quite filled yet, right? Like, but it still gets removed from the 4 first. So, if we were doing the opposite, maybe this goes along with your question too, like in this case, if you're removing from this scenario, they're both 2s, P's higher than S, you would remove from the P, if they're the same number. But if they're different numbers, always go with the higher one first. So, did that answer your question, Zach?
Yeah.
Yeah, great question. Have a smile face for that. Any other questions on this? Alex?
Is the order for like the S and P, is it in order of like the periodic table, so it'd be like S and then F, P, P, or how does that work?
Like, oh, in terms of like energy.
Which one is the highest?
Well, the thing is with the D and the F, they're always out of order, so it's only ever going to be comparison of P and S. Because those are the only 2 that will like line up and be the same.
Okay.
Does that make sense?
Yeah.
Because like, for example, if I did something that went through it, it's going to be like 6s2, it goes down to 4, and then 5, and then back to 6. And so in the end, these are the only 2. But,
Gotcha.
so, I guess if there was, like, because as of right now, there's no such thing. Yeah, but I see what you're asking though.
4 and 14. My favorite.
Any other questions? Now, I do want to say one thing just notation-wise, because I think on your quiz tonight, you'll see it. Some people choose to write a configuration in order of number. And so they would actually write, like, let's say, like, so if this is my configuration for 6p2 lead. okay, you could possibly see it where they actually would rearrange it and do it like this. And they put it in the order of the numbers. It's not my preferred way to do it, which is why I didn't teach it to you that way, but just be aware, like there's one on your homework where they put all the D's, all the 3's, they put 3S, 3D, and 3P, like all by each other versus the 4S in between. But recognize they're all there, it's just they put it in number order. So, okay, let's look now at the experimental proof behind this crazy notation stuff. So as we just mentioned, if you put energy into an atom, you can get the electrons to jump. Well, if you put a whole bunch of energy in, such as X-rays, you not only get them to jump, but you can get them to fly out of an atom. So you can literally rip off the electrons from an atom using this method. And that's the idea of spectroscopy, is putting energy in to it, different varying depending on what energy you're looking for. Okay? So the idea here is that X-rays are shown, and these are like high intensity X-rays, so not even like the same magnitude of X-rays that are used for like if you were to get an X-ray. Okay? High powered X-rays go into the atom. They're so high energy that when this electron absorbs it, bing, it comes flying off. And then if you just keep adding energy, it just keeps shredding. I don't want to break my model, but like the electrons just keep shredding from the outside in. As they come off, and based on how much you had to pay, gives you indication of how tightly they were held. So we have this thing known as the binding energy, which is the force at which the electrons are held to an atom. And this is going to be something that we talk about a lot today with this idea of positive and negative forces. And really all year, a lot of chemistry is about positive and negative things. Okay? So if I have my atom here, right, so the red ones, doesn't really matter which ones, but the protons are in the middle, they're positive. The electrons are out here, they're negative. Okay? There's a force of attraction between them because positives and negatives. Now there's other forces that go on, which is why they don't just like get sucked into the nucleus. But you should understand there's a force of attraction. I sometimes nickname it the love. There's a love that the nucleus has for its electrons. Okay? Now attractive forces, whenever you're dealing with positive and negative things, goes back to Coulomb's law. Has anyone ever heard about Coulomb's law before in another science class? And I don't blame you if you haven't. I blame your teachers, just kidding. It's fine. So Coulomb's law is a fundamental thing about positive and negatives. That positive and negative is influenced by two factors. Okay, these are going to be the words of the day. Okay, magnitude and distance. But we'll actually bring in vector later of the direction because it's kind of the same idea. Okay, so the magnitude of it influences the attractive force, and the distance influences the attractive force. Meaning, the more protons I have here, that's the magnitude. If I add more protons, that's more love that they're going to feel. Less protons, less attractive force. Okay? Distance is how close they actually are to the nucleus. So don't say anything out loud, but just to kind of put together what I've been saying, are all electrons loved the same by the nucleus? If love represents the attractive force. Don't say anything out loud. Or could you point to me on my model of which electrons are loved the most? Raise your hand if you have an idea of which ones are loved the most. Zach, who feels the most love?
The ones on the inside.
Why?
Because they're closer to the nucleus, and if they're closer, they get more love.
Yeah, distance, right? If the distance is closer, there's more attractive force, right? Okay, so the closer they are, the more force they feel, aka the more binding energy. So what this means here is that if it takes a lot of energy to pull an electron off, then that must mean there was a lot of force holding it on in the first place. Right? You can kind of think of energy as like payment, right? Like if I have to pay you a lot, it's because there was a lot of force holding it there to begin with. Okay? So when we look at our graphs here, do we get this filled in? Okay, we're gonna get these little peaks spread out. This is an example, and I'll go to another one that you haven't. This one's not in your notes, but here's just an example of what a graph looks like after we've stripped an atom of all its electrons. Okay, is we get the binding energy is the the x-axis, and then the amount of electrons is your y-axis. Okay. Is everyone okay if I go on? I just want to use the example that's on your notes. Okay, so look up at this graph with me here. So the first thing you want to do when you look at these graphs is identify which peak has the most binding energy. Now these graphs can be a little weird sometimes in the scales because they can flip-flop. In this case, it started at 0 and went higher, but I just want you to be aware, and I hate that they do this, but if I go back really quick, sometimes they can do it the other way around, where 0's on that side and it gets higher this way. I wish they'd just pick one and stick to it so it doesn't flip-flop, but the idea is the same. Is we want to find the one with the highest binding energy first. Okay, because the higher the binding energy, okay, so BE means the closer to the nucleus. So between our two peaks here, looks like peak number 2, right, has a higher binding energy. Everyone see that? So that means it must be the closest to the nucleus. So what orbital is always the closest to the nucleus? So label that peak. It must be the 1s, because 1s is always the closest. So first orbital, first subshell is always the 1s. After that, as I go lower in binding energy, it just follows the pattern. So what always comes after 1s? 2s. So this peak, label that one, must be the 2s peak. So far with our configuration, we have 1s and 2s. Now the height of the peak is telling you how many electrons were that energy value. So in this case, this one had 2, so it would be 1s 2, and this would be 2s 1. Which then helps me know that it must be lithium. So you can use this method to identify an unknown element. Questions on how I did that? Now, just once again, because graphs can look different, this one specifically told you like the height of the peak, 2 and 1, right? Let me go back to this example. This one didn't. Sometimes they don't. Sometimes they'll just have like lines on the side that indicate it. Sometimes it's somewhat assumed because you know the 1s always is, like if there's more peaks, this has to be filled. And the most that can be in the s is 2. And so you know, okay, that is the height of 2, and then you can figure out the rest. So just kind of be aware of that. But any questions before we try a practice problem? Okay, did we fill that in? Did I skip that too fast? Okay, fill that in really quick. It just goes over what we talked about. So as you go back, puts into just on paper what we just did. So once again, it's about the highest binding energy, because then it helps us identify from the core outward what it is. Okay, once you fill that in, go ahead with your team at your table. Try these 2 practice problems on the back side, and then we'll check it for 2 smiley faces. Okay, ready, set, go. Talk it over as a group.
I got the EP biology.
Oh, I didn't.
I wanted to get into this. Yeah, so then I went to the
Okay, give me a wave if you want another minute before I go over the answers. Kind of walked around and it seemed like everyone was ready. Okay, if you said that this first one is aluminum, have a smiley face because you're correct. And you're not get aluminum and don't understand why. Okay, and then for this one, I don't remember where the answer. Neon, I think. Is that right? Yeah. Neon. Questions on interpreting photoelectron spectrums? Not too bad, hopefully, once you know what they're at. So that's what your quiz 1.6 is about. There's going to be some questions that are like these, where you're identifying an unknown. There's other ones that are actually going to have you compare two different elements, graphs to each other, and kind of ask you questions about that. The biggest thing I'd say for now, because I don't want to give you the answers, because I want you to think about it, but just remember what binding energy represents. And if something has a greater binding energy, what does that tell you about it? Okay? All right, so what we're going to go into now, turn your page. There's one last little thing we're going to write in our notes, and then we'll jump into our activity we're going to do today together. Okay? Now, in learning this last topic, it's going to look a little bit different, as you can already see, in how we're going to learn it. But what I want you to understand is, first off, I'm not just like sending you out to sail on your own. I'm still here to help you. I'm just doing it in a different way to get your brain to think differently. Because just like our muscles, where it's valuable to work out your muscles in a variety of ways, it's beneficial to your brain to work it out in a variety of ways. Right? With muscles, that's how you get certain injuries, is because you do the same thing over and over again. Right? Or that's why you plateau, is because you do the same thing over and over again. Right? In order to improve in something, you have to apply stress to it. So today might feel a little more stressful than other times, but no, it's because we're helping you learn, and I'm still here. Okay, I'm still going to help you. We're going to make sure we're on the right track. It's just going to look a little bit different. Okay, so go ahead. Let's fill in these notes, and then we'll look at that white packet. So the big thing of today, as I mentioned, is this idea about positive and negative attraction in the Coulombic law. Okay, so Coulomb's law is all about that the interaction between two electrical charges is based on the charge, which is the magnitude of it, and the distance between them. Okay, in our activity today, you are going to be discovering different trends and patterns on the periodic table, and then justifying why those trends happen. Okay, the key word here is eventually we're going to do this without data. We're going to look at data today to identify the trend, but once you know what the trend is, you shouldn't need data anymore, because you know, oh, well, it increases in this direction, so it must be bigger. Okay? And then on the justifying side, the key thing is it should always come back to Coulomb's law. When I come around to pass you off at various stop signs, you're going to have to make sure that this is a connecting piece to it. Okay? All right, let me show you two models that you can label to help you visualize what we mean. So this model represents magnitude. Okay, and the difference of how magnitude influences attractive force. If you want to label this one as this is your magnitude example. Okay, so here's force of attraction. Okay, notice force of attraction is getting bigger because you have more protons, right? More protons means more magnitude, more love. Right, so there's a greater attractive force the more protons something has. Person.
Is this like constant across all every atom, every proton and stuff?
Like constant in terms of this value?
Like the value.
I don't know if I can say yes or no to that. But I can say the more protons will always make magnitude go up. I would assume that possibly some other things might play into it, but I'll have to look because I can't say with 100% certainty yes. But great question. This model represents distance and its influence over attractive force, right? So notice that attractive force goes down as distance goes up, right? So there's less attraction the further they are away. Just like if you had two magnets, right? If you put them far away, they're not going to feel much of a pull. Versus as you bring them closer together, you can literally feel them starting to pull on each other. Okay? All right, in our activity today, you do have assigned roles because I find that helps things be more productive as well as gets everybody involved in the process, which has value. Okay, once again, everything I do has reason, it has value, so hopefully you'll see that in this activity as well. Okay, so I'm going to go through what the different roles are. I gave a paper, like 2 papers to each table, so you can kind of look at it as you go in case you forget. So go ahead and pass out. I put on your table, there's packets, so everybody take a packet. It says periodic trends, and then there's 2 of these papers, so you kind of put 1 on each side just to look at as you work. There's nothing like here you have to do. That's just kind of an instruction direction sheet. Okay? All right, so you guys get to be the lucky chosen table. We're going to use you to model the different roles with everybody else, okay? So everyone look over here because you're going to orient yourselves in the same way, okay? So if you are in this position right here, you're going to be the first reader/clarifier. Now the roles will rotate, so if you don't like it, you won't be there forever, okay? So the reader's job, number 1, is to obviously read the questions, read any information that's given out loud so you're as a group. Okay, but the second part with the clarifier is the reader should make sure that you don't go on until everyone's had a chance to put their answer down. So don't read the next question if someone's still writing, right? Let's be considerate of others, let them finish their thought before you move on. As well as is if someone seems confused about the answer, like they don't have anything, okay, your job is to clarify and make sure everybody knows where we're at before you move on. Okay, so that's the reader's job. Okay, the person next to them, right here, you're going to be the first floor manager, okay? So the floor manager's job is right after the reader speaks, you are the first to answer every time, okay? So they're going to read the question, and you get the opportunity to share your thoughts about the answer, okay? Do your best. If you're, like, unsure, that's fine, okay? But you're going to try first. After you try and say, I'm not sure, then it can open up to the rest of the group, but don't just default say, I don't know, right? Give it a try, okay? The other job of the floor manager is to, once again, make sure that the airtime is being distributed well, right? That everyone's being involved in the process, okay? All right, the person straight across from them is the questioner, okay? Their job is to make sure that any answer someone gives has reason behind it, because you may say, oh, the answer's 36, and in your head, you know why you said 36, but if you don't say it out loud, the questioner's going to say, where did you get that from? How do you know that? Even if the answer doesn't say to justify, we want to make sure we understand where things are coming from. Okay? So that's the questioner's job. And then this person right here, you are the, what do I call you? Big idea person. So your job is that when you get to the stop sign, I know this up, Soraya. So you'll notice once you get through the first page, there's a little stop sign at the bottom. So once you get to the stop sign, the big ideas person's going to raise their hand. I'll come over, and you're going to pass off to me, did we get what we were supposed to get? This is where I'm not leaving you hanging. I want to make sure we don't walk away today with anything you weren't supposed to learn or missing anything. Okay, so big ideas person, before you raise your hand, if you need to summarize with your group to make sure you know before you raise your hand, that might be a good idea, but they're going to summarize for me. Once they do that, okay, so notice underneath there's a little checklist for each page. Everyone see that on this list here? Okay, so the first one is complete page 1 according to the following responsibilities. Raise your hand when you're ready to get signed off. Okay, I'll give you a green light once I say, yep, we understand it, we got what we needed to. You're then actually going to go to your notes, and there's a certain section of your notes you'll fill in. This is how we're doing notes today too. But you don't do this until you call me over, because we don't want to write down things that are wrong. Okay, so I'm making sure we're right. Okay. Once you fill this out, there's then a practice problem. Everyone look at the bottom of 21. See that practice problem down there? This is then like your test. Okay, you've learned it. We've discussed it. Can you apply it? So you're going to answer this practice problem as a group. without the data in your packet. Okay, so just using the periodic table, answer this, raise your hand a second time, I'll come check. If this is right, then that means we should be on the right track. You then are free to move on to the next page and rotate roles. So then that's when roles will change, is once you pass the stop sign. So it's kind of like we got to do a double stop here at every stop sign. Stop, check that we have the information, do a practice problem, check again, and then I'll give you the green. Questions on that process? Okay, just to make sure, we're going to do a little acting here with this table. Are you guys ready? It's okay.
Oh no.
And so everyone else follow along in the packet, but just to model like kind of how to start and how to get going, we're going to have this group help us out. Okay, so reader, Gavin, will you read the opening theme for us and just question number 1? Everyone follow along with him.
The periodic table is often considered to be the best friend of chemists and chemistry students alike. It includes information about atomic masses and element symbols, but it can be used to make predictions about atomic size, electronegativity, ionization, energies, bonding, solubility, and reactivity. In this activity, you will look at a few periodic trends that will help you make those predictions. Like most trends, they are not perfect, but useful just the same. Consider the data in Model 1 on the following page. Each element has 3 numbers listed under it. Which value represents atomic radius?
Okay, so everyone turn to Model 1. You're going to use this model a lot. This is your data. Okay, so now Soraya, you get the opportunity because you're the floor manager. It said of the 3 numbers listed in that model, can you tell them which one is the atomic radius? No, you're okay. And there's nothing wrong, once again, with the floor manager of like, hey, I'm not quite seeing it. Does anyone else see it? It's just getting started. No, that's okay. So Brissa noticed, so there's a little code here at the bottom. Everyone see that? Right? So the code kind of just goes in order of each of these setups. Right? So which one is the atomic number according to our key down here? Or if we're looking at hydrogen, what would be its atomic number? Or I mean atomic mass, not number. 37. So the first number listed underneath it represents the atomic radius. Does everybody see that? So these first questions are kind of just getting you oriented with this table. Okay, so then everyone would go back to the front page. You'd write in 37. The question asker would maybe ask if it wasn't clarified, like, hey, how'd you get 37? Right? Like, if you weren't sure. Okay? Then once everyone has their answer, yeah, go ahead, Jeff. Yeah, you can go along with this group. I'm just getting you started, and then we'll set you all loose. Gavin, will you read one more for us? Once you get your answer written. Oh, and check that your rest of your group has their answers written.
Who's Gavin?
I'm Gavin.
Why did I call you Gavin?
His name's Daniel.
I'm sorry, Daniel. When we moved seats, it all of a sudden messed up my brain. I apologize, Daniel. Will you read the next one for us? Once everyone gets their answer written.
What are the units for the atomic radius?
Talking about like the numbers.
Close, so not the number itself, but the unit that's associated with the number.
So it says that it's the unit that is used is PM. If you look down to the key, it says next to atomic radius PM between parentheses.
So everyone see it. Sorry, I just said this. You look down at the key, next to atomic radius is this thing PM, stands for picometer. That's okay if you didn't know what that was, but that's just what the unit of what they're measured in. It's just a very, 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 very small measurement. Okay? Good so far? Okay. So then you would just continue the process with the reader, floor manager. Once again, they're not the only one speaking, right? It's just getting the conversation started with someone, but they're welcome to be like, I'm not sure. What do you guys think? Okay, talk as a group. Move on to the next one. Once you get to the stop sign, call me over. Or if you have questions beforehand, you can call me over too. Okay? Any questions before we get going? Yeah. You need one. I'll grab you one of those so you can look at it too. Okay, let's give this group 2 claps for their performance. And you can each have 3 smiley faces. Thanks for helping me out. Okay, ready, set, go.